In 1801, the sudden disappearance of a newly discovered dwarf planet triggered an astronomical crisis. Yet, the mathematical breakthroughs forged to relocate Ceres did far more than solve a 19th-century mystery. They birthed the foundational algorithms underpinning our modern digital world. Join us as we explore how a 2-century-old cosmic hunt forged the very computational tools powering today's artificial intelligence. We navigate our modern digital world using 2-century-old starlight. Every time a machine learning algorithm trains, a GPS satellite pinpoints your location, or your phone filters out background noise, your devices execute mathematical tools forged during a state of absolute scientific panic in 1801. Behind today's most advanced technologies lies a timeless mathematical foundation born directly from a historic astronomical crisis. On January 1, 1801, astronomer Giuseppe Piazzi spotted a new celestial object in the constellation Taurus, fulfilling a bold mathematical prophecy. Sitting at 2.8 astronomical units from the Sun, it landed precisely in the missing planet gap predicted by the Titius-Bode law between Mars and Jupiter. Piazzi named his discovery Ceres, sparking widespread celebration across the astronomical community as a triumph of mathematical prediction. Just 41 days after its discovery, disaster strikes as Ceres vanishes into the blinding glare of the Sun. With Piazzi falling ill, the planet is officially lost. Astronomers now face a mathematical nightmare. They manage to capture a mere 9 degrees of its orbit. Calculating the remaining 351 degrees from this tiny, error-riddled sliver of data is deemed mathematically impossible. Confronted by the lost world, the scientific establishment completely surrenders. Renowned mathematician Pierre-Simon Laplace declares the sparse, noisy data impossible to analyze. Meanwhile, philosopher G.W.F. Hegel publishes a treatise invoking Plato's magic numbers to argumentatively prove that no planet could ever exist in that gap anyway. With both mathematics and philosophy admitting defeat, the hunt for Ceres seems officially over. Where the scientific establishment sees an impossibility, a 24-year-old upstart rejects defeat. Enter Carl Friedrich Gauss, a young mathematician from Brunswick who boldly ignores philosophical proofs and classical limitations. Focusing on just 3 of Piazzi's 22 messy observations, from January 1, January 21, and February 11, Gauss invents entirely new mathematics designed to extract the true signal from the noise and solve the unsolvable. To solve the impossible, Gauss sparked a fundamental paradigm shift. Where 18th-century thinking rigidly assumed circular orbits and discarded errors as useless noise, producing fragile equations that failed, the Gaussian paradigm embraced uncertainty. By treating orbits as dynamic, unknown ellipses and mathematically modeling noise directly into the equation, Gauss built a robust framework capable of extracting truth from imperfect data. To overcome this challenge, Gauss forged his first breakthrough weapon, the method of least squares. Rather than forcing a perfect curve through imperfect observations, he minimized the sum of the squared errors between the raw data and the predicted path. By minimizing these deviations, a clear, best-fit orbit emerged directly from chaotic, noisy measurements, forever transforming how we extract truth from imprecise data. Next, Gauss forged his second weapon, the truth filter, known today as the bell curve. Recognizing that measurement errors follow a predictable pattern, where small mistakes are frequent, large ones rare, and all are symmetric, he mathematically modeled human imperfection itself. Utilizing the law of probable errors, Gauss filtered out observational noise to pinpoint the single most likely truth hidden within flawed telescope readings. To overcome the grueling task of solving an 8th-degree polynomial, requiring over 100 hours of manual calculation, Gauss unleashed his secret weapon, computational decimation. While tracking asteroids in 1805, he devised a divide-and-conquer algorithm to interpolate trigonometric series, drastically dropping computational time from n squared to n log n. In doing so, Gauss quietly invented the fast Fourier transform 160 years before its celebrated rediscovery in 1965. By December 1801, Gauss puts his new mathematical arsenal to the ultimate test, publishing his predicted ephemeris for the lost planet. Armed with least squares and the bell curve, he shocks the scientific establishment by directing the celestial police to an entirely different region of the night sky, directly contradicting the leading models of the era. With his precise coordinates locked in, Gauss places a high-stakes bet on the power of his revolutionary mathematics. In December 1801, data achieved a definitive triumph over philosophy. Astronomers von Zach on December 7 and Olbers on December 31 pointed their telescopes precisely to the coordinates Gauss dictated. There, glowing in the dark, Ceres was recovered within half a degree of Gauss's prediction. The lost fugitive planet was finally restored, cementing a new era for mathematical precision. Gauss didn't just find a rock drifting in space. By resolving the Ceres emergency, he achieved something vastly more consequential. He invented the foundational mathematics for extracting pure signal from chaotic noise. That single breakthrough transformed how we separate truth from static forever. From starlight to silicon, the mathematical innovations of 1801 directly power our modern world. The method of least squares now drives artificial intelligence, machine learning, and predictive modeling. The Gaussian distribution serves as the bedrock of modern statistics, economic forecasting, and error analysis. Meanwhile, the fast Fourier transform powers digital signal processing, Wi-Fi, audio compression, and global telecommunications. What began as a quest to locate a lost planet became the linchpin matrix sustaining 21st century technology. This is the invisible architecture of our modern world. Every time we train a neural network, filter a digital signal, or follow a GPS route, we rely on the exact same fundamental calculations. What began as a 19th century quest to locate a single lost rock in the dark now forms the hidden framework guiding us through the chaos of the 21st century.